Hi, I'm Pasquale, and this presentation is about our CLIA paper titled Complex Query Answering with Neural Link Predictors. And this is joint work with Eric, Daniel, and Michael. So let's consider this setting. We have a knowledge graph, a graph-structured knowledge base where knowledge about the world is represented in the form of relationships between entities. In a knowledge graph like this one, nodes correspond to objects in the world, or also abstract concepts, and edges correspond to relationships between these. In this example, we have a knowledge graph about biomedical entities, which tells us that paroxetine is used to treat anxiety and as vasodilation as a biological action, and that apixaban treats deep vein thrombosis, and one of its pharmacological effects is that it's an anticoagulant. Now, one problem with real-world large-scale knowledge graphs is that they are often incomplete. In this particular case, we are missing a link stating that apixaban is a medication, that deep vein thrombosis is a disease, and that apixaban can have side effects when taken together with paroxetine. A very effective solution to identifying missing links in large knowledge graphs is via neural link prediction models. In neural link prediction, the underlying idea is that we can learn an embedding vector for all the nodes in the graph. For example, in this case, we will learn an embedding vector for apixaban, paroxetine, vasodilation, deep vein thrombosis, and all other entities in the graph. Now, assume we want to know the type of relationship, if any, between apixaban and paroxetine. The likelihood that two entities, in this case apixaban and paroxetine, are linked by a given type of relationship, in this case interacts, is a function of the embedding vectors of the source node, in this case apixaban, and the embedding vector of the target node, in this case paroxetine. And we can use this function for ranking missing links and find out that, for example, apixaban is likely to interact with paroxetine, even if this link is not directly available in the knowledge graph. Now, consider the problem of answering complex queries on incomplete knowledge graphs. Here we have a query: which medications have side effects when taken with drugs for treating anxiety? And we want to have a list of medications that answer our query. This query can be formalized in logic form, and it reads as follows. Find M, where M is a variable, such that there is a D, which is also a variable, such that M interacts with D, and D treats anxiety. Note that this is just an example, and our method supports arbitrarily complex logic queries with conjunctions and disjunctions. Now, the best solution for solving this problem proposed so far is the following. First, we automatically generate millions of complex query answer pairs. And then we train a deep neural network to produce the correct answers given the query. The neural model works as follows. First, we represent the complex query as a graph, where each node corresponds either to a variable or to an entity in the query. Then the graph is processed through a deep neural network, which will return a ranked list of answers. Now, there are two main problems with this approach. One is that training is extremely expensive, since the models need to be trained on millions of generated queries. Also, it's not really clear what happens if we evaluate on queries that differ from the queries that we used for training. Another issue is that there is no explanation for the reasons why a given answer was predicted. To solve these problems in this work, we propose a completely new paradigm for answering complex queries on incomplete knowledge graphs. We first train a model phi for answering simple atomic queries, like which drugs treat anxiety. And then we convert each query into an optimization problem, where we need to identify the optimal values of the variables, in this case M and D, in the query, that maximize the likelihood of both that M interacts with D and the likelihood that D treats anxiety. Then those two likelihoods are aggregated using a T-norm, which is a continuous relaxation of the logical end from fuzzy logic. And depending on whether we search for the best values of M and D in a discrete or continuous space, we can cast this problem as either as a continuous or a discrete optimization problem. In the discrete case, we want to identify the best mapping from variables to entities that maximizes the score of the query. We experimented with a very simple greedy approach to solve this problem. We first start with the variable D and search for the k most likely values for D by finding the top k treatments for anxiety according to the neural link prediction model. Then, for each of the candidate values of D, we identify the most likely values for the variable M. And then we compute the query score for all generated pairs of values for M and D, and return the most likely values for M and D. Another approach we experimented with consists in directly optimizing the vector representations associated with the variables M and D. This can be done via gradient-based optimization. We first initialize the embeddings of M and D randomly, and then we optimize the embedding of M and D to maximize the score of the query. And finally, we replace the embedding of M with the embedding of all the candidate entities and rank them using the corresponding query score. So we experimented on a variety of complex query structures. And despite being only trained on simple queries, we can see that our model systematically generalizes to complex queries better than models trained on complex queries in the first place. Here are the results on Freebase 15K237 for different complex query types. Here we can see the results on Freebase 15K. And here the results on L995. And here we have the average results between all types of complex queries that we considered. And we can see that our model produces significantly more accurate results on all the three datasets. This improves over existing models, both in terms of the data efficiency, because we only need to train our model on a much smaller dataset of simple queries, and also in terms of out of distribution generalization, because we get better generalization accuracy on complex queries without having to train on them in the first place. Another really nice feature of this model is that it can provide explanations for its predictions. Other models in this space only return a list of answers to the query. For instance, in this case, the answers being produced are apixaban, amitriptyline, duloxetine, and others. Our model can also be used to provide the intermediate results associated with each query in the form of the variable assignments used to produce the answer. For example, here we can see that apixaban and amitriptyline were considered as answers because, according to the model, they interact with paroxetine. While duloxetine was considered as an answer because, according to the model, it interacts with pregabalin. And this allows us to check whether the results are being produced for the right reasons. In this case, paroxetine and pregabalin are two possible treatments for anxiety, so the model is producing the correct answers for the correct reasons. This is not always the case. For example, consider the following query from Freebase 15K237. What international organizations contain the country of nationality of Thomas Aquinas? Here, the model was able to return the correct set of answers: NATO, OECD, EU, and WTO. However, these were returned for the wrong reasons. Thomas Aquinas was mistakenly assumed to be from the US, from the UK, or from Germany, while the correct nationality of Thomas Aquinas is Italian. Our model enables us to detect such errors and possibly correct them by refining the underlying neural link prediction model. So, to summarize, in this paper, we propose a new approach for answering complex queries on large scale and incomplete knowledge graphs. In our approach, we first train a neural link prediction model on the task of answering simple atomic queries. And then we cast the problem of answering complex queries as an optimization problem, where we need to find the mapping from variables to entities that maximizes the score of the complex query. And we show that our approach generalizes extremely well to complex queries, despite not having been trained on them in the first place. All the source code, the pre-trained models, and the datasets are online at this link. And if you want to collaborate on this topic or have any questions or comments, please feel free to reach out to us. And thank you for listening.